Alkynes Part 2. Preparation and properties of alkynes. Preparation has been discussed. So now we are discussing the properties of alkynes. Some of the properties has been discussed in the first part, and second part it is addition reactions. So usually here one important thing is to be discussed. Alkynes are having a triple bond between the carbon atoms, and alkenes are having a double bond between the two carbon atoms. So it looks like that alkynes are having the two weak pi bonds and one sigma bond. Here only one pi bond is there. So actually, alkynes looks like the very rich source for the electrophilic attack. So that what we expect is alkynes are actually more reactive than the alkenes because of the availability of the more electrons towards the electrophilic addition reaction. But in reality, alkenes are more reactive than the alkynes. Let us see the reason why. See, whenever you take alkyne, I am taking the general alkyne R C triple bond C R dash. So whenever electrophile is ready to attack over the alkyne and forms a complex like this intermediate compound electrophile, because electrons are there, pi electrons are there. So this is an intermediate compound that is formed when alkynes are participating in the electrophilic addition reaction. So later nucleophile will attack. That is the different task. Nucleophile may attack or this position or that position to open this particular structure. Imagine if it attacks over this particular position, so that we will get this type of this structure. R dash. But in the case of the alkenes, if you take C double bond R dash and we shall take like this R double dash and R triple dash. Just I am taking a general alkene. So when electrophile is attacked over this double bonded carbon atoms, it forms an intermediate structure which is far more stable than the one intermediate structure formed in the case of the alkynes. And later nucleophilic attack will be there, and that will be the different task. So to open the mechanism pattern looks similar, but the stability of the intermediate differs from alkynes to the alkenes. So here we already the nucleophile R double dash and R triple dash. So here intermediate is formed, here also one intermediate is formed. The intermediate that is formed in the case of the alkene is stable, and the intermediate that is formed in the case of the alkyne is unstable. So due to the formation of the unstable intermediate, alkyne is not ready to be converted to the an unstable compound, so that generally it do not participate chemical reactions like alkenes. So that's why alkynes are generally less reactive than the alkenes. This is the only reason. So now let us see some of the addition reactions. Then everyone knows that addition of hydrogen is called as the hydrogenation. So let us see the first reaction. Addition of hydrogen. So it is also called as the hydrogenation. Hydrogenation reaction, or simply it is called as the reduction reaction. We know that alkynes, this reaction has been discussed in the alkenes part. you take an alkyne and subject to the hydrogen in the presence of the catalyst. This catalyst varies, that we shall discuss now. So once 1 mole of hydrogen is added, one hydrogen one side, another hydrogen other side, and break one bond. So it becomes CH2 double bond and CH2 alkene. So this one again on reaction with the 1 more mole of the hydrogen in the presence of the catalyst will be finally completely be converted to the saturated molecule. So initially alkyne on reduction initially gives alkene. I am writing the general name, not their IUPAC name. And finally it gives the saturated hydrocarbon, that is alkane. So these catalysts are different types that we had already discussed in the alkanes topic. So one such a catalyst I will give you, that is Lindlar's catalyst. I am just giving the rough information about Lindlar's catalyst: palladium, calcium carbonate or barium sulfate plus quinoline. Even acetic acid also will be there. This complete combination including acetic acid is called the Lindlar's catalyst. And there is one more catalyst, that is sodium liquid ammonia or lithium ammonia. Means instead of the sodium we can take the lithium also. Lithium ammonia in the presence of the ethyl alcohol, or else you can use the lithium aluminum hydride as the reducing agents. And apart from this you can use the one more catalyst, that is platinum oxide. Generally this catalyst we don't discuss. So platinum oxide, or you can take C6H5 taken thrice, phosphorus taken thrice. This is a catalyst. So if you are using any of these catalysts, first catalyst, Lindlar's catalyst, gives the alkynes will be converted to the cis alkenes, and this one gives the trans alkanes. Means both of these catalysts, they reduce the alkyne to the alkene, means partial reduction takes place, not the complete reduction. Then what is the use of this catalyst? This catalyst is usually helpful in reduction of the higher alkynes. Whenever the larger alkynes are there, big size alkynes, so that higher alkynes will be directly converted to the alkanes, not the alkenes. Even in the case of the catalyst, you can use the nickel, platinum or palladium. If these metals you are using, then you don't get the alkenes as the product, you get directly alkanes as the product. Alkanes are the final products, means complete reduction takes place. So let us see some of these reactions initially. So we shall take one by one. R, C triple bond C, R plus H2, subject it to the Lindlar's catalyst. Lindlar's catalyst, or palladium, calcium carbonate, even quinoline also, plus quinoline. So we get the molecule like this. This is R, hydrogen, hydrogen. So this is a cis alkene. And if you subject the same molecule with the sodium liquid ammonia or lithium aluminum hydride, then we don't get the cis alkene, we get the trans alkene. So the molecule is like this: R, hydrogen and hydrogen. So it is trans alkene. Okay, and the same molecule, if you think this is a higher alkyne, and if it is subject to the platinum oxide or else simply nickel platinum or palladium plus H2 in combination with the hydrogen. Anyhow, hydrogen is there, no? So that hydrogen separately not necessary to write down here. So you get directly the alkane molecule, means R CH2 CH2 R. If you take R dash here, it will become R dash. So complete reduction will be there. So these two catalysts, they partially reduce the alkynes to the alkenes, whereas this particular combination means separately you have to take platinum oxide is separate combination, and either any of these metal with the hydrogen is a separate combination. So if you subject with this catalyst, directly you will get the alkane as the final product. Now let us see the addition of halogens. Addition of halogens. So here acetylene combines with, I will take acetylene, means acetylene is a general example. So acetylene combines with the chlorine in the presence of the CCl4. So one chlorine will be added to the one side and another chlorine another side. So we get the CHCl double bond CHCl. Now again you add the chlorine in the presence of the CCl4. You break one more bond and add chlorine here and there. So you will get the CHCl2 and CHCl2. So if you write down the name of this particular molecule, here 2 chlorine atoms, here 2 chlorine atoms. So just give the numbering. So at first position 2 chlorine atoms, at second position also 2 chlorine atoms are there. So we can write 1, 1, 2, 2 tetrachloroethane. 1, 1, 2, 2 tetrachloroethane. Popularly, this molecule is known as Westron. So, in objective questions, they used to ask the Westron. So, Westron means this is the tetrachloroethane means, or simply it is also called as acetylene tetrachloride. Acetylene tetrachloride. Okay. So, this molecule means partial halogenation means this particular molecule will get. Complete halogenation means we get this type of the molecule. Now, let us see with the propane, the same type of the reaction with the propane. We just take the CH3, C triple bond CH. This is a propane plus Br2 CCl4. So here CH3, hydrogen, bromine and bromine. So you can expect why we are getting this type of the molecule. Why? Because the concept has been discussed over here. See, opening. After opening, you are getting the actually the location of these electrophile and nucleophile are opposite to each other. So we may say that is a trans product. So here we are getting the trans product, initially trans product, and when again it is subjected to the one more mole of the bromine in the presence of the CCl4, then you cannot say that the next molecule is a trans product, because trans cis combination we can say only in the case of the alkenes, not in the case of the alkanes. So you have to add one more bromine here and there. So the molecule finally becomes bromine, and here also bromine, and here also bromine, here hydrogen. So the name of this molecule is 1, 2, 3. So 1, 1, 2, 2 tetrabromo tetrabromopropane is the molecule. Now, thus alkynes actually from this reaction, it is very clear. The important thing of this reaction is not, anyhow this has been discussed in the alkenes topic. Bromine is a colored liquid. It is a we know that a reddish brown colored liquid. Okay. So this color will be decolorized. So alkynes decolorizes bromine. Hence this reaction is helpful in identifying the presence of unsaturation. Because saturated molecules cannot decolorize the bromine liquid. So bromine liquid will be decolorized by both alkenes as well as the alkynes. So it is helpful in identifying the only presence of unsaturation. So here I will take the two reactions which are important reactions. So I request you please do remember these reactions. CH triple bond CH. I am taking the ethyne acetylene, because this reaction has been asked many times that ethyne on reaction with the liquid bromine. They mention like this. And the other side they have mentioned like this, bromine water. Okay. When you take the pure liquid bromine, then all these bonds will be broken, and here two bromine atoms will be added, so that we get the CH-Br2 single bond and CH-Br2. It is a tetra, means 1, 1, 2, 2 tetrabromoethane or acetylene tetrabromide. But when bromine water is added, only partial halogenation takes place. Means only one bromine will be added, so that only one bond will be broken. So we get the CH Br double bond and CH Br. So partial bromination takes place in the case of the bromine water, and liquid bromine means complete halogenation takes place. Hence I say that this reaction is important. Now let us take the another reaction, that is iodine. Generally iodine reactions are not useful. Why? Because iodine react very slowly with the alkyne or acetylene, but iodine reacts with the acetylene in the presence of the alcohol. So we can write alcohol, you can take ethyl alcohol also. So the molecule will be CHI double bond CHI. This is the final product, because two iodines cannot attack, because the molecule that formed itself is unstable molecule, so cannot react with one more mole of the iodine to make it the molecule still more unstable. So that's why this reaction is stopped at this particular stage. Now let us see the addition of halogen acids. Even these videos are available. I am sharing to you. Whenever you have the doubts, you can check these videos. Addition of halogen acids. So here generally alkynes in the sense, I will take acetylene as the best example for all these reactions. So acetylene on reaction with the HBr, we can say that this is a symmetrical alkyne. This is an unsymmetrical reagent. So unsymmetrical reagent has to be divided into two parts, H plus and Br minus. So you add hydrogen here and bromine one side. So imagine that we are getting the CH2 double bond CHBr. Now there is chance for the addition of one more mole of the HBr, because the addition reaction will continue to take place till all these pi bonds are broken, or unsaturation completely converted to saturation. Now this is an alkene which is unsymmetrical. This is a reagent which is unsymmetrical. So both are unsymmetrical substances. So when unsymmetrical alkene is added to the unsymmetrical reagent, then we can apply the Markovnikov's rule. Hence I can say that the Markovnikov's rule is applicable over here, and in that cases H plus N will be added to the double bonded carbon with more number of hydrogen, so that hydrogen will go and add over here, and bromine will go and add over there, so that the molecule finally will get the CH3 Br2. So this is called as ethylidene bromide. You must remember certain names. This name, ethylidene bromide, means two bromine atoms are in the same carbon atom. Ethylidene bromide. And here I forgot to say one thing, that the reactivity of the halogens towards the acetylene is, alkynes is, chlorine is more reactive than the bromine, which is more reactive than the iodine. Just remember this particular reaction. Okay. And let us take one more molecule, propyne. So every time we take one example as acetylene, the other example as the propyne. Plus HBr. So now you add the hydrogen here and bromine there. Why? Because now it is an unsymmetrical alkyne. So unsymmetrical alkyne and unsymmetrical reagent, again Markovnikov's rule is applicable over here. So that we can say that CH3, CBr, double bond CH2, and add one more mole of the HBr, so that the molecule again CH3, CBr, and Br, here it is CH3. So the molecule name is 2,2 dibromo propane, and for this molecule, if you add hydroiodic acid, we will get the molecule like this, CBr and iodine and CH3. And if we add HCl as the next step reagent, then the molecule will be CH3, CBr, chlorine and CH3. So pattern and procedure, everything is same. Now what happens if peroxide is used? So just see, I will take the peroxide effect also here. Acetylene, just add HBr initially, so that we get the CH2 double bond CHBr. The name of this molecule is vinyl bromide. So when this vinyl bromide is subjected to the addition of one more mole of the HBr in the presence of the peroxide, you no need to use the peroxide helper, heat, electricity, peroxide, light, everything, anything if used, then next reaction is opposite to the Markovnikov's rule, means hydrogen will go and add over here and bromine there. So you will get the CH2Br and here also CH2Br. So it is called as the 1,2 dibromo ethane. Okay. So apart from this, some particular reactions, they not necessary to use only HBr. For example, they may mention like this also, hydrochloric acid and Hg+2. So you should not become panic by seeing this type of the things. They are just as the catalysts. So they increase the speed of the reaction. So products are same. That is, now we are getting the vinyl chloride. So do not become panic by seeing these reactions and catalysts. So now let us see addition of another particular reagent, that is addition of hypochlorous acid. So hypochlorous acid means HOCl is called as the hypochlorous acid. So in this particular case, you see here, I forgot one more thing, that the rate of reactivity of the hydrogen halides towards the alkene is hydroiodic acid is more reactive than the hydrobromic acid, which is more reactive than the hydrochloric acid than the hydrofluoric acid. So this is the way they react actually with the alkynes. Now let us see how the hypohalous acid react with the alkynes. So I'll take the as usually two alkyne, different alkyne, that is, one is acetylene. So acetylene on reaction with the HOCl, In HOCl, OH minus gets the partial negative charge, chlorine gets the partial positive charge. So that positive charge one side and OH part other side. Imagine we added the chlorine here and OH there. So the molecule becomes double bond CHCl and here OH. Now if you see one important thing in this particular case, vinyl part means whenever OH group is added to the double bonded carbon, it becomes unstable, so immediately it participates in the tautomerism. Or else you can go for the one more step also, like this HOCl. Again you add the OH here and Cl there, so that we get the molecule like this. So whenever two OH groups are present on the same carbon atom, the molecule is unstable, it loses immediately the water molecule, so that we get the CHO and CHCl2. So it is called as 2,2 dichloroethanol, means here it will get the first position because aldehyde group, this is the second one. So 2,2 dichloroethanol or acetaldehyde. Now let's take the propyne. CH plus HOCl. So where to add OH part, where to add the chlorine? Chlorine is being a positive charged one, goes and adds to the carbon with more number of hydrogen, unsaturated carbon with more number of hydrogens. So that we get the CH3, COH, double bond CHCl, and here you can add one more molecule, or just you can go directly for tautomerism also. Again you add HOCl because again still unsaturation is there. So here you will get the CH3, I'll write like this to make it more easy, and here CHCl2, remove one water molecule. So you will get the CH3, here C with oxygen, so you just develop the double bond and CHCl2. Now it is from this side you will give the number 1, 2, 3. If you give from this side also, CO part will get the 2, but this part will get the last number, so that you preferably give from this side. So it is 1,1 dichloroacetone or 1,1 dichloropropanone is the IUPAC name. Similarly, let us take the addition of sulfuric acid also. These are all just addition reactions. Only one thing is we need to split up the reagent into two parts. So addition of sulfuric acid. So in addition of sulfuric acid, we know that H2SO4 is the molecule that splits up into H plus and HSO4 minus. So in this way we have to split up. You should not make it a 2 H plus and SO4 minus 2, because at a time we can break the only one pi bond, so that one species can be added. See, if you take the acetylene like this and add H2SO4, because two hydrogens it is able to provide, you cannot take the two hydrogens at a time. Only one hydrogen, that too concentrated sulfuric acid. Add one hydrogen here, HSO4 here. So you will get the CH2 double bond CH HSO4. This is the part. This is called as the vinyl hydrogen sulfate. Vinyl hydrogen sulfate. Okay. This particular part is called as the vinyl part, and this is the hydrogen sulfate. Again there is unsaturation still, so that we can add one more molecule of the sulfuric acid, that is concentrated sulfuric acid. But generally in examination they no need to mention separately that they are going to add the 2 moles of sulfuric acid. Once they mention the concentrated sulfuric acid, means 2 moles are there. So that add hydrogen here, because it splits up into two parts, H plus and HSO4 minus, and this is unsymmetrical alkene, this is unsymmetrical reagent. So according to the Marconi capsule, positive part of the reagent will be added to the double bonded carbon with more number of hydrogens, so that we get the CH3 here. And next one is HSO4 now taken twice. This is called as ethylidene hydrogen sulfate. Ethylidene hydrogen sulfate. So why to use the ethylidene? Ethylidene in the sense, whenever two species, same species are added to the carbon atom in the ethane molecule, this is called as the ethylidene part. Like CH2 double bond CH is called as vinyl. So CH3 CH2, this particular part is called as the ethylidene. Okay. So if bromines are there, it is called ethylidene bromide. If chlorines are there, it is called ethylidene chloride, like that. Okay. Similarly, let us take the one more continuation reaction for this. The thing is, if we add water to this particular ethylidene hydrogen sulfate, so HSO4 parts in organic chemistry, whenever water is added, wherever HSO4 part is there, that will be removed as H2SO4, because H plus ion from the H2O will be added to the HSO4 and will be removed as the H2SO4, and remaining OH part of the H2O will be connected to the carbon from where HSO4 part has been removed. So here two HSO4 parts are there, so that two water molecules, so that we get the CH3 CH OH, this is one part, this is OH another part. So here there is a loss of one water molecule like this, and we get the CH3 CHO. So finally we get the acetaldehyde. Acetaldehyde. So this is the one reaction. Now let us see the addition of the water, that means hydration. Addition of water, hydration. So it is simple thing that water alkynes generally cannot be hydrated easily like alkenes. So that is the reason why we need the help of certain catalysts like sulfuric acid and mercuric acid, like that. So in the case of the hydration of the alkynes, we use 40% of the sulfuric acid, and here we use the 1% of the HgSO4. So in chemical reaction, whenever you take the alkyne like this, so alkyne with, they may take H plus, Hg plus 2, H2O, or else they may say that alkyne plus H2O. Here they may just use H plus and Hg plus 2. Okay. So Hg plus 2 means in HgSO4 mercuric sulfate, it dissociates and gives Hg plus 2 plus SO4 minus 2. H2SO4 dissociates and gives the H plus and HSO4 minus. So this particular part they may mention. So no need to mention complete formula of the catalyst in this particular cases. So that you must be careful while selecting the reagents and while seeing the compounds. Now let's see some of these reactions. Ethyne or acetylene on reaction with the 40% of the sulfuric acid, 1% of the mercuric sulfate. This is important one. You must remember that. Important combination. So add hydrogen one side, OH other side. So we get the CH2 double bond CH OH. Okay, this is called as vinyl alcohol. Vinyl alcohol is completely unstable. So we know the reason. The reason is OH part is added to the double bonded carbon atom. It immediately undergoes tautomerism, a type of isomerism. So that we get the CH3 CHO, acetaldehyde. Okay, and I am going to discuss one more important compound. You see here CH3 C triple bond CH. This is ethine, this is propane. So propane with H2O, same combination of the catalyst. Hg plus 2 is the catalyst, not the H2SO4. You must remember that. Okay. So here this unsymmetrical alkyne, unsymmetrical reagent. So H plus will be added to the unsaturated compound with more number of hydrogen. So here we what will get CH3 C double bond CH2. So OH part will be added here. Again this molecule is unstable. I forgot to write down unstable here. This is unstable. So here this is also unstable. The reason being is it is connected to the OH part is connected to the double bonded carbon. So immediately it undergoes tautomerism. Tautomerism is a type of isomerism which had been discussed in our reaction mechanism. So tautomerism, so that we get the CH3 C double bond O CH3. This is acetone. So the purpose of discussing this particular reaction is many times the question has been asked about this one, that only acetylene is the molecule on hydration gives aldehyde. So aldehyde will be given only by this one, ethine, acetylene. Other alkynes you take, whether it is terminal alkyne or internal alkyne, apart from the ethine, this is ethine. You take any type of the alkyne, you will get the ketone. See, this is the ketone part. So to clarify this point, I'll take one more alkane. I'll move like this because all these molecules will be visible to you. So I'll take one more molecule, CH3 C triple bond CCH3. Let's take butane, add H2O in the presence of the same 40% H2SO4 and 1% mercuric sulfate. This is symmetrical one, this is unsymmetrical one. Just add hydrogen one side and OH other side. So CH3, imagine OH is added here, double bond CH, CH3. Again I am going to write down this is the one that is unstable. Okay. So here because OH is added to the double bonded carbon. So again it undergoes the tautomerism. So this is tautomerism. Just rearrangement of the atoms takes place. Tautomerism is also a type of the functional group isomerism. But once you are considering it as a functional group isomerism, we should not call it as a tautomerism. So we have to call it as either tautomerism or functional group isomerism. So here also you can see what type of the functional group has been raised, ketone again. This is the molecule butanone. It is also ketone. So you take any type of the alkynes on hydrolysis, hydration, they produce the ketone except ethine, which produces aldehyde molecule. Okay. Now let us see another type of the in this particular case even temperature also has to be used. That means simply I forgot to mention, you just put the heat in the sense 70 degrees centigrade. Heating process. Okay. So next one, addition of hydrogen cyanide. Addition of HCN. Just like water molecule, this is also unsymmetrical reagent. So that I'll take CH triple bond CH plus HCN, hydrogen cyanide. This process takes place in the presence of the barium cyanide. So hydrogen one side, cyanide other side. So we'll get the CH2 double bond CHCN. We all know that this particular one is called as the vinyl, and here cyanide is there. So it is called as the vinyl cyanide. So vinyl cyanide, or it is also called as the acrylonitrile. So in examination they follow this particular name, not the vinyl cyanide, acrylonitrile. So this acrylonitrile on polymerization gives the polyacrylonitrile. This had been discussed on polymerization, which I am not going to discuss here actually. So even if you want, you see here how the polymerization takes place. So I'll write this molecule here separately. So separately I'll write down that molecule. CH2 double bond CHCN. This CN do not participate in the reaction, only this unsaturation. So again you take the same molecule in the same pattern, CH2 double bond CHCN. Again you take the molecule CH2 double bond CHCN. You must be, you observe, which is very careful observation. So polymerization, on polymerization, it is an addition polymerization, so that here pi bond shifts between these two carbon atoms, this pi bond shifts between these two carbon atoms, this pi bond shifts between the carbon and another molecule, and here also it gets one bond from this side. So you can write the molecule like this, hyphen, because the bond is coming from the other molecule, and the CH2 single bond CH, where cyanide is there, connected to the CH2 single bond CH, cyanide, connected CH2 single bond CH, cyanide, like this. It will continue. The process will continue to take place like this. So in this particular process, what did you observe? This is the one that is completely repeated many times. So this cyanide will go up here, so it repeated n number of the times, and this particular molecule is called the polyacrylonitrile. PAN, polyacrylonitrile. Now let us see the addition of acetic acid. Addition of acetic acid, we know that acetic acid dissociates to CH3 COOH, which is acetic acid, dissociates to CH3CO minus plus H plus. You should not write actually complete dissociation because it's a weak acid. So anyhow, we need these species. So you just take the ethyne molecule, add acetic acid in the presence of Hg plus 2 and 80 degrees centigrade. So H plus one side, CH3CO part other side, CH2 double bond CHO, C double bond O, CH3. And this reaction, this particular molecule is called as the vinyl acetate. Okay. So this vinyl acetate on reaction with the one more mole of the acetic acid CH3 COOH in the presence of the same catalyst Hg plus 2 at 80 degrees centigrade. Again you add hydrogen here and acetate part over here. So the molecule will be CH3 CHO, C double bond O, CH3 O, C double bond O, CH3. So I said already with you that this particular part is called as ethylidene. So the name of this molecule is ethylidene acetate. Ethylidene acetate. This ethylidene acetate continuation reaction, we can write many reactions. If it is heated, if you heat this ethylidene acetate, just I will pull it down. So you heat it because it is a little bit unstable molecule. So if you heat it to the approximately 300 to the 400 degrees centigrade, then the thing happens here is we get the acetic anhydride like this CH3COOCH3 means it will be split up like this CH3COOCH3. So which on combination produces CH3 C double bond O C double bond O CH3 acetic anhydride, and next what is left behind here CH3 CHO. This is acetaldehyde. So we are getting the aldehyde as well as the anhydride when use the acetylene molecule. Now let us see addition of alcohol. So in addition of alcohol generally will be added to the alkynes in the presence of NaOH or KOH. So CH triple bond CH acetylene on reaction with the C2H5OH. So here oxygen carries the partial negative charge, hydrogen carries the partial positive charge. In the presence of the actually HgSO4 and NaOH or KOH, anything you can use along with the mercuric salt. Okay, so here hydrogen will be at one side and ethoxy part will be added on the other side. So you will get the CH2 double bond CHOC2H5, and this particular molecule on hydrolysis it breaks the bond here. So hydrogen here, OH here. So you will get the molecule CH2 double bond CHOH plus ethyl alcohol, and here tautomerism takes place because this is a vinyl alcohol. So the molecule takes place like this CH3 CHO. So we are getting the acetaldehyde. Instead of ethyl alcohol, let us take methyl alcohol. Both are same because here you may ask me the question that sir, can't we add one more ethyl alcohol? As we can add. If you add ethyl alcohol here instead of the water molecule, then this will not be the final lab product. So hydrogen here, ethoxy part over here. So here CH3 CH O C2H5 and here is O C2H5, and this molecule on hydrolysis in the presence of the H plus acid hydrolysis, ethers will be converted to the simply alcohol part. So here we will get the CH3 CH OH and OH, and carbon with 2 OH groups is unstable, loses one water molecule, and finally produce again this molecule, that is CH3 CHO acetaldehyde. Here also we got the acetaldehyde. Okay. So we can use, if you take the methyl alcohol, here you will get the CH3 parts. If you take the propyl alcohol, here you will get the C3H7 part. Now let us see the ozonolysis of the these alkynes. Addition of ozone. Simply it is called as ozonolysis. So alkynes on reaction with the ozone in the presence of CCl4, they form the ozonide. The ozonide here it is different. I am going to discuss that particular part also here. So I will explain one part here. If you take the alkene ozonides we have already discussed. Just I am comparing both of these reactions in the presence of the CCl4 here. You break two bonds. Whenever you are adding the ozone, you need to break the two bonds between the carbon atoms. So here CH2, oxygen, oxygen, oxygen. Just connect like this. This is the ozonide in the case of the alkenes. Here also we are adding the ozone to the unsaturated molecule. Here also ozone is breaking the two bonds. So two pi bonds are broken out of three bonds. So that's why one more bond is left behind here. So this particular ozonide, this is the difference between the alkenes and alkynes. Ozonide and on zinc H2O, it may be reduced to ozonolysis or oxidative ozonolysis, you will get the similar products. Let us take the reductive ozonolysis. So on reductive ozonolysis, you will get this particular bonds will be, means this bond will not break. Carbon-carbon bond cannot be broken, only these bonds will be broken. This particular bond, this particular bond. So it will get the CHO and the CHO, and this H2O becomes H2O2. I think you got my point. Whatever the water is there, water is oxidized to the peroxide. So when you are using the oxidative ozonolysis or reductive ozonolysis, the products in the ozonolysis of alkynes is same. Why? Because this particular peroxide will oxidize the carbonyl compound formed into the carboxylic acid. So it breaks this bond and it will be formic acid and it will be oxidized to the formic acid. So we get the 2 moles of the formic acid. So similar example I'll take, and general example I'll take R C triple bond C R dash plus ozone in the presence of the CCl4. Okay, so you write down the ozonide C here R dash. This is the ozonide, and use the zinc H2O. We feel this is reductive ozonolysis, but it becomes automatically oxidative ozonolysis. So initially reductive cleavage takes place. So here what happens, R C double bond O C double bond O R dash plus H2O2. This H2O2 plays major role because peroxide, this particular peroxide oxidizes the formed ketone or aldehyde into their respective carboxylic acid so that it breaks up this particular bond. So we get the RCOOH plus R dash COOH. So that's the reason why whenever you are taking the alkyne molecules, whether you follow reductive ozonolysis or oxidative ozonolysis, final compounds are carboxylic acids. So these are the carboxylic acids which we are going to obtain mainly. So now let us see certain type of the polymerization reactions. These polymerization reactions are also known as the self-addition reactions or else polymerization reactions. Self-addition reactions. Or these reactions are also known as the polymerization reactions. So based on the number of alkyne molecules participate, they are called as the trimerization, tetramerization, like this. So if 3 molecules are participated, that is called as the trimerization. If 4 are participated, tetramerization, like this. The simple thing is, we'll take one by one molecules. You take the 3 alkyne molecules, acetylene, and pass this acetylene gas through the red hot iron or copper tube. Red hot in the sense it will be around 600 to 700 degrees centigrade. So when you pass this acetylene gas through the red hot iron or copper tube, we get the benzene. I'll write down that molecule how we are going to get the benzene. CH triple bond CH, CH triple bond CH, and here also CH, triple bond CH. You see, when this acetylene is passed through 3 acetyl molecules, I have taken combination is same. So one of this pi bond will shift over here, and this pi bond will shift over here, and this pi bond will shift over there. So finally the molecule becomes here CH is there. Now one bond lost, so the double bond is there, CH. Now here single bond, here double bond, CH. Next again single bond, here next CH, which is having the double bond, CH, single bond here. So it is nothing but the benzene molecule. Okay. So instead of acetylene, means it is the one of the method of the preparation of the benzene. So instead of the acetylene, if you use the propane, CH3C triple bond CH, 3 molecules of propane and the same red hot iron copper tube. So here an extra CH3 is there, no? That extra CH3, you remove one hydrogen here, put CH3 here, and similarly remove one hydrogen here, put CH3, and remove one hydrogen here, put CH3, means CH3 CH, here CH part is there. So CH3 part is placed over the carbons alternative to this triple bonded carbon. So like that you will get the molecule benzene like this, with CH3 groups are located on the alternative positions. This is called as the mesitylene. It is called as the, means one name is 1, 2, 3, 4, 5, 6. 1, 3, 5 trimethyl benzene is called as the mesitylene. So out of if you send 4 acetylenes instead of 3 acetylenes, then the molecule will, polymerization molecule will be different. Let us take the 4 CH triple bond CH acetylene. Now we are not using the red hot iron tube, we are using the anhydrous nickel cyanide. This is a bit important, you must remember that, nickel cyanide, and use the high pressure. So in that cases you need to add the molecule like this, CH, double bond CH, double bond CH, double bond CH. Why I put the double bond? Other bond is shifted, like in the earlier case. Here we have shifted now. Like this we need to shift. So after shifting we need to add one more single bond. So this is the molecule which is called as cyclooctatetraene. Cyclooctatetraene is the molecule. Thank you dear students. Hope if you understand my explanation, comment, like and share this video, subscribe the classroom point.